In November of 2025, thousands of people saw a headline claiming Mount Rainier was about to erupt. It wasn't. What actually happened next reveals something far more unsettling than a false alarm. It reveals just how little warning we might actually get when the real thing happens. The mountain at the center of that headline sits 54 miles from downtown Seattle, a peak of ice and rock that most people who live near it simply call the mountain, as if there were no other one worth naming. On a clear day, it fills the entire southern skyline, rising more than 14,000 feet above sea level, its summit wrapped year-round in snow and glacial ice. Tourists photograph it from ferry decks. Runners use it as a landmark on the horizon. For most of the year, it looks less like a threat and more like a postcard. And yet, for a few days last November, that postcard became the center of a very real, very fast-moving scare. But underneath that postcard is one of the most dangerous volcanoes on the planet. Not the most dangerous because of how often it erupts, and not because of the size of its explosions. To understand why scientists watch Rainier so closely, you have to understand what it's actually made of. It isn't just rock. Rainier carries more glacial ice than every other volcano in the Cascade Range combined. 26 named glaciers cling to its slopes, filling valleys and crowning ridgelines in ice that, in some places, is hundreds of feet thick. That ice has been accumulating for thousands of years, slowly compacting, slowly moving, slowly carving the mountain into the shape we now recognize. It's beautiful. It's also, geologically speaking, a loaded weapon. Here's why. When a volcano like Rainier becomes active, it doesn't need a massive eruption to become catastrophic. It just needs enough heat to start melting ice. Hot gas, rising magma, or even a landslide of weakened rock can be enough to trigger sudden violent melting on the upper slopes. That meltwater doesn't just trickle downhill. It mixes with ash, mud, boulders, and debris to form what geologists call a lahar, a fast-moving slurry with the consistency of wet concrete, capable of traveling at speeds that rival a car on the freeway. Lahars are the reason Rainier tops nearly every list of dangerous American volcanoes, even though it hasn't had a major eruption in centuries. The valleys that drain the mountain's glaciers, the Puyallup, the Nisqually, the Carbon, the White River, are not empty wilderness. They are home to tens of thousands of people. Entire towns, including parts of Orting, Puyallup, and Sumner, sit directly on top of ancient lahar deposits, some of them more than 500 years old, some far older than that. The ground beneath entire neighborhoods, entire school districts, entire shopping centers, is literally made of the last time Rainier's ice melted in a hurry. And it has done that before. Around 600 years ago, in the mid-1400s, Rainier produced its last confirmed eruption. Before that, geological records show at least a dozen eruptions over the last 2,600 years, along with dozens of lahars that didn't necessarily require an eruption at all. Some of the largest lahars in Rainier's history happened without any volcanic explosion whatsoever. All it took was enough of the mountain's summit rock turning to weak, hydrothermally altered clay, saturated with heat and water until gravity did the rest. One of these events, thousands of years ago, sent a wall of mud and debris all the way to what is now Puget Sound, more than 50 miles from the summit. Seattle itself, in some areas, sits on top of lahar deposits, estimated to be as much as 600 feet thick in places. That's the scale we're talking about. Not lava creeping across a field, not an ash cloud drifting over a city, a wall of mud, ice, and rock, moving up to 50 miles an hour, capable of reaching populated valleys in under an hour, in some cases, in as little as 30 to 45 minutes from the moment it begins. So when people saw headlines in late 2025 claiming that Rainier was showing new signs of activity, it's understandable why so many reacted with alarm. The story spread quickly. Online, a seismic monitoring station near the summit had detected what looked like volcanic tremor, the kind of shaking associated with magma or fluid moving through cracks deep inside a volcano. Volcanic tremor is a real and legitimate warning sign. It's one of the exact signals scientists look for when trying to determine whether a volcano is waking up. But this time, it wasn't that. When the United States Geological Survey looked closer, they found the signal was coming from a single high-elevation station, and only that station. No other instrument on the mountain was picking up anything unusual. When their scientists investigated the hardware itself, they found the real cause. Ice had built up on the station's antenna, distorting their radio signal being transmitted back to monitoring centers. The tremor wasn't coming from inside the volcano. It was coming from frozen equipment struggling to communicate through a Pacific Northwest winter. The Pacific Northwest Seismic Network, which works alongside the USGS to track earthquakes across the region, confirmed there was nothing unusual happening beneath Rainier at all. In an average month, the mountain produces around 9 small earthquakes, so minor that most people living nearby would never feel them. would never even know they happened unless a seismologist pointed them out. A few times a year, that number spikes into what's called a seismic swarm, a cluster of small quakes occurring in rapid succession over a few days. These swarms have been documented for decades and are generally explained by ordinary processes, like groundwater and hydrothermal fluids moving through existing fractures deep in the rock. They are not considered precursors to an eruption. They're simply part of what a large geologically active mountain does when nobody's paying particular attention. The false alarm made headlines, briefly, and then it faded. But it left behind a strange and useful lesson. The gap between the mountain moved and the mountain is about to erupt is enormous, and most people, understandably, have no way to tell the difference from a headline alone. That gap is exactly where confusion, fear, and misinformation tend to grow. And it's also exactly the gap that scientists at the Cascades Volcano Observatory spend every single day trying to close. So what does real monitoring actually look like at a volcano like Rainier? It's not a single sensor waiting for something dramatic to happen. It's a dense, overlapping network designed to catch the earliest possible signs of change, long before anything visible occurs at the surface. Seismometers are scattered across the mountain, constantly recording ground motion sensitive enough to detect earthquakes far too small for a human to feel. GPS stations anchored into bedrock track the ground's position down to fractions of an inch, watching for the slow uplift that can indicate magma accumulating beneath the surface. Gas sensors monitor for changes in volcanic emissions, since a rising body of magma often releases gases like sulfur dioxide before an eruption becomes visible. Stream gauges track the temperature and chemistry of rivers flowing off the glaciers, watching for signs of heat or altered mineral content that might suggest something changing underground. All of this data flows in continuously, 24 hours a day, every day of the year, feeding into the Cascades Volcano Observatory and the Pacific Northwest Seismic Network. Scientists don't wait for a crisis to start paying attention. They're already watching, always, which is precisely why they were able to identify the November 2025 tremor signal as equipment interference within a relatively short window, rather than letting public alarm build for weeks. As of the most recent weekly updates from the observatory, Rainier remains at what's called normal alert level, with a green aviation color code, the lowest and calmest tier on the scale. That doesn't mean the mountain is silent. It means the specific kind of activity being recorded, small earthquakes, minor debris flows, background noise, falls within the range of normal behavior for a large glaciated volcano. In the most recent update, sensors picked up small earthquakes at both Rainier and its neighbor to the south, Mount St. Helens, alongside a minor debris flow in one of Rainier's creek drainages. None of it triggered any change in alert status. None of it suggested unrest. It was simply the mountain doing what large volcanic mountains do, shedding rock, shifting ice, settling under its own enormous weight. This alert system exists precisely because volcanoes rarely erupt without warning, at least not volcanoes as closely monitored as the ones in the Cascade Range. Before Rainier could erupt, the alert level would almost certainly climb in stages. An unusual pattern of earthquakes, a burst of ground deformation, a spike in gas emissions, any of these might prompt an information statement from the observatory. If unrest continued or intensified, the alert could move to advisory, then potentially to watch or warning, each stage representing a higher confidence that an eruption is approaching. This isn't guesswork. It's built on decades of comparative data from volcanoes around the world that have gone through this exact process before erupting. That system is reassuring, but it isn't the whole story, and this is where the deeper unease about Rainier really comes from. The system is built to catch magmatic unrest, activity tied to rising magma. But Rainier's most catastrophic historical events, the massive lahars that buried valleys and reached Puget Sound, didn't always require magma to move at all. They were triggered by the slow, silent weakening of rock deep inside the mountain, a process called hydrothermal alteration, where circulating heat and acidic fluids gradually turn solid volcanic rock into something closer to wet clay. This process can happen over centuries, invisibly, until a trigger, an earthquake, heavy rainfall, or simply gravity reaching a tipping point, sends a slope collapsing without any classic eruption warning signs at all. This is part of why Mount Rainier is officially ranked by geologists as one of the top 3 most dangerous volcanoes in the entire United States, alongside Kilauea in Hawaii and Mount St. Helens, its neighbor just south. The ranking isn't primarily about how violently or how often these volcanoes erupt. It's about a combination of eruptive potential and, more importantly, how many people and how much infrastructure sits directly in harm's way. 11 of the 18 Icarius volcanoes classified as very high threat in the United States sit in Washington, Oregon, and California, in large part because of exactly this pattern. Explosive, ice-covered mountains looming directly above dense, growing population centers. Rainier isn't alone in the Cascades either. To its south sits Mount St. Helens, the most frequently active volcano in the range. still remembered for its catastrophic 1980 eruption that killed 57 people, flattened hundreds of square miles of forest, and blew nearly 1,300 feet off the summit in minutes. St. Helens erupted again in the mid-2000s when a new lava dome slowly grew inside its crater over several years, a quieter kind of eruption than 1980, but a clear reminder these mountains are not dormant relics. To Rainier's southeast sites Mount Adams, Washington's largest active volcano by volume, though far less famous than its neighbors. Adams recently drew headlines of its own when seismic activity there ticked upward, prompting concern online. Scientists were quick to explain the increase still fell within normal background seismicity for the mountain. But Adams carries its own version of Rainier's danger. It hasn't erupted in roughly 1,000 years, yet its ice-capped summit conceals large volumes of the same hydrothermally weakened rock that makes catastrophic landslides possible, without warning, capable of reaching communities below at speeds up to 50 miles an hour, without a single drop of lava ever reaching the surface. Put these mountains side by side, Rainier, St. Helens, Adams, along with Mount Baker and Glacier Peak further north, and a pattern becomes impossible to ignore. This isn't a single dangerous mountain sitting in isolation. It's an entire chain of active ice-covered volcanoes stretching through one of the most densely populated corners of the Pacific Northwest, each one capable of producing hazards that don't require a dramatic eruption to become deadly. And yet, life around these mountains goes on almost entirely undisturbed. Millions of people live within sight of Rainier. Over 2 million visitors hike its trails and photograph its glaciers every single year. Ski resorts operate on the slopes of Baker. Communities have grown, decade after decade, in valleys that geological surveys have literally mapped as lahar hazard zones because the land is fertile, the views are extraordinary, and the danger, most days, feels abstract. It's a risk measured in centuries, not headlines, and human memory simply isn't built to stay afraid of something that hasn't happened in 600 years. That's precisely why moments like the November 2025 false alarm matter so much. Even though the tremor turned out to be nothing more than ice on an antenna, they're a reminder of just how quickly attention can spike, and just how quickly it fades once the explanation turns out to be mundane. For a few days, Rainier was in every feed, every conversation, every worried text message between people who live in its shadow. Then the explanation came out, the alarm dissolved, and the mountain went back to being scenery. But somewhere beneath that scenery, the actual, slow, patient geological processes never stopped. Magma continues to exist beneath Rainier's summit, as it has for thousands of years. Groundwater continues to circulate through fractured rock, slowly altering its structure. Glaciers continue to grind against volcanic stone, reshaping slopes millimeter by millimeter. None of that shows up as breaking news. None of it trends. And yet all of it is exactly the kind of activity that one day, without necessarily any dramatic warning at all, could set a lahar in motion down one of these valleys. This is the strange tension at the heart of every story about Rainier. On one hand, the science is reassuring. The monitoring network is dense, sophisticated, and constantly improving. The alert system is designed specifically to catch unrest long before an eruption. And history shows that most volcanoes, including this one, tend to give warning before anything catastrophic happens. On the other hand, Rainier's greatest historical disasters weren't always eruptions in the traditional sense. They were collapses, landslides, and lahars, triggered by processes that don't always trip the same alarms. So where does that leave the people living in its shadow and the rest of us watching from a distance? Somewhere between vigilance and calm. The current data, as of the most recent observatory updates, shows nothing unusual. Alert levels remain normal. Aviation codes remain green. The small earthquakes recorded in recent weeks fall squarely within the range scientists consider background noise, the same kind of activity Rainier has produced for as long as instruments have existed to measure it. There is no evidence right now of an eruption building beneath the surface. But normal doesn't mean irrelevant, and quiet doesn't mean safe forever. Rainier's history makes one thing unmistakably clear. This mountain will erupt again. Every geologist who studies it says some version of the same sentence, not as speculation, but as near certainty, built on 2,600 years of geological record. The only real question, the one nobody can answer with any confidence, is when. It could be centuries from now. It could be sooner. The mountain itself keeps no calendar that we've been able to read. What we do have is one of the most advanced volcano monitoring systems on the planet, watching that mountain every second of every day, translating tiny tremors and subtle shifts in the ground into data that scientists can actually interpret. What we have is a documented history, stretching back thousands of years that tells us almost exactly what this volcano is capable of, and almost exactly which valleys would bear the weight of it if the worst ever happened. And what we have, for now, is quiet. Small earthquakes here and there, a minor debris flow in a creek bed, ice occasionally freezing over a sensor and sending a false signal into the world. It's easy to look at a headline calling Rainier the most dangerous volcano in Washington, and imagine something on the verge of erupting, smoke curling from a crater, evacuation sirens sounding in the valleys below. The reality, at least right now, is quieter than that, and in some ways more unsettling for exactly that reason. There's no visible drama, no plume, no glow on the horizon at night, just a mountain of ice sitting on top of a volcano that has erupted a dozen times in the last few thousand years, being watched by instruments sensitive enough to catch a whisper of movement deep inside the rock, waiting, the way it has for 600 years, for whatever comes next. And maybe that's the real story here, more than any single tremor or false alarm. It's not that Rainier is about to erupt. The evidence simply doesn't support that, not today. It's that an entire region has learned to live comfortably, almost casually, in the presence of something capable of reshaping the landscape within the span of an hour. Cities were built on top of its old lahars, without most residents ever learning that fact. Trails wind across slopes that scientists have identified as unstable. Ski lifts run above ground that, geologically speaking, is still actively forming. None of this is meant to suggest constant fear is the answer. Fear, especially fear built on misunderstood headlines, doesn't actually make anyone safer. What makes people safer is exactly what the scientists at the Cascades Volcano Observatory do every single day. Watching closely, communicating clearly, and correcting the record fast when a story gets ahead of the facts, the way it did in November of 2025. It's a quiet, unglamorous kind of vigilance, mostly invisible until the one moment it isn't. There's also a human side to this story that rarely makes headlines, and it might be the most important part of all. In the valleys below Rainier, communities have spent decades preparing for a scenario nobody wants to imagine. Towns like Ording sit almost entirely within a mapped lahar hazard zone, close enough that, in a worst-case event, residents might have as little as 30 to 60 minutes to reach higher ground before a mudflow arrived. Local emergency planners built one of the most advanced volcano early warning systems in the country, a network of acoustic flow monitors along the river valleys that can detect a lahar in motion and automatically trigger sirens throughout the community. Schools in these valleys run lahar evacuation drills the same way schools elsewhere run fire drills or earthquake drills, teaching children from a young age exactly which route leads to safe, elevated ground, and exactly how quickly they need to move if the sirens ever sound for real. It's a strange kind of normal, growing up practicing an escape from a disaster that hasn't happened in 600 years. But the drills exist precisely because waiting to figure out the plan after a siren sounds would already be too late. Emergency planners describe minutes, not hours, as the realistic window for evacuation in the valleys closest to the mountain. And that tight timeline is exactly why the drills, the sirens, and the marked evacuation routes exist long before any sign of unrest appears. There's a broader lesson buried in that kind of preparation, one that extends well beyond Rainier itself. Communities living near active volcanoes anywhere in the world tend to fall into one of two patterns. Some ignore the risk almost entirely, treating a quiet mountain as a permanently safe one, right up until it isn't. Others build the danger into daily life, not through fear, but through preparation, drills, sirens, and clearly marked escape routes that become so familiar they stop feeling like emergency planning and start feeling like just another part of living somewhere beautiful and slightly dangerous at the same time. The towns around Rainier have largely chosen the second path, and it's part of why, even amid genuine geological risk, there isn't widespread panic simmering beneath the surface of daily life in the Puyallup or Nisqually valleys. It also helps to understand how Rainier compares to other famous volcanoes people picture when they imagine an eruption. Most people picture something closer to Hawaii, slow rivers of glowing lava creeping across open land, dramatic but rarely deadly because of how predictable and gentle the flows tend to be. Rainier is an entirely different kind of mountain, a stratovolcano, steep and cone-shaped, built from alternating layers of hardened lava, ash, and rock, the same category that includes St. Helens, Mount Fuji, and Vesuvius. Stratovolcanoes produce far more explosive eruptions than shield volcanoes like Kilauea, and when that force meets a summit loaded with glacial ice, the hazard becomes something else entirely, fast, unpredictable, and capable of devastating areas many miles beyond the mountain itself. Climate change adds another layer of complexity, one scientists are still working to understand. Rainier's glaciers have been retreating for decades, like glaciers nearly everywhere, losing thickness as temperatures climb. Less ice could theoretically mean less meltwater available to fuel a massive lahar during a future eruption. But retreating glaciers can also expose and destabilize slopes previously locked in place by ice, potentially increasing landslide risk even without a volcanic trigger. Researchers are actively studying how these shifting conditions might change the mountain's hazard profile over coming decades, a reminder that even a well-understood volcano still holds questions nobody has fully answered. None of this uncertainty translates into imminent danger, and it's worth repeating that clearly, because uncertainty and danger are not the same thing. The current monitoring data, gathered from seismometers, GPS stations, gas sensors, and stream gauges scattered across the mountain, shows nothing consistent with an approaching eruption. The alert level remains normal. The aviation code remains green. Scientists aren't withholding concern behind a calm public message. They're reporting exactly what the instruments show, because that's the entire point of building a monitoring network this dense in the first place, to replace guesswork and rumor with actual measurement. That distinction matters more than almost anything else in this story. A headline can spread in minutes, built on a screenshot or a single unusual data point, stripped of context. Real volcanic monitoring takes patience, cross-referencing dozens of instruments against decades of historical baseline data, and resisting the urge to sound an alarm before the evidence supports one. The scientists who caught the November 2025 false alarm didn't guess. They checked every other station on the mountain, found nothing unusual anywhere else, and traced the anomaly to a very unglamorous cause: ice interfering with a radio antenna in the middle of winter. That's ultimately what responsible monitoring looks like. Not dramatic announcements, but quiet, methodical verification, week after week, year after year, mostly unnoticed until the rare moment it becomes essential. It's the same quiet vigilance that keeps evacuation routes marked, sirens tested, and drills scheduled in towns that have never actually needed to use any of it. It's preparation built for a threat measured in centuries, maintained by people who understand that the absence of an eruption today says nothing about tomorrow, next year, or the next several centuries after that. So the next time a headline claims Washington's most dangerous volcano is stirring, it's worth remembering what that actually tends to mean. Sometimes it means ice on an antenna. Sometimes it means a handful of small earthquakes well within the range this mountain has always produced. And sometimes, eventually far down whatever timeline the mountain is quietly following, it will mean something real. The instruments are built to tell the difference. The scientists are trained to interpret it. The communities in the valleys below have built sirens, drills, and evacuation routes around exactly that possibility. And the mountain itself, for now, remains precisely where it has always been: quiet, immense, and patient, holding 26 glaciers and centuries of geological history above a region that has learned carefully and deliberately how to live in its shadow without living in fear of it. There's one more thing worth sitting with before this story ends, and it has nothing to do with seismographs or gas sensors. It has to do with scale and with how strange it is that a structure this powerful can sit so quietly beside one of the fastest growing metropolitan areas in the country. Millions of people wake up within view of a volcano capable of reshaping the map around it, and for almost all of them, that fact never crosses their mind. The mountain becomes wallpaper, a backdrop for photographs, a landmark for directions. That kind of quiet coexistence isn't naive, and it isn't reckless. It's what happens when a genuine, well-documented risk gets absorbed into ordinary life, filtered through decades of monitoring until it stops feeling like a looming threat, and starts feeling like just another fact about where you live, the way people near the coast learn to live with hurricanes. The danger doesn't disappear, it becomes something managed, something watched. And that, in the end, might be the most accurate way to describe Rainier's current status: not dormant, not awakening, but simply being what it has always been. A mountain built from repeated eruptions across thousands of years, a reservoir of ice above valleys full of people. A slow, patient system of rock, heat, and water that occasionally sends a tremor through a seismograph without crossing into anything the instruments call unusual. Nothing about the science right now suggests an eruption is close. Everything about the mountain's history suggests one is coming eventually. Both of those things are true at once. Which brings the story back to where it started, that one frozen antenna in November of 2025, and the far more unsettling question it left behind. The tremor turned out to be nothing, but for a few days, before anyone traced the signal back to ice on a piece of hardware, it looked exactly like the kind of data that could precede something catastrophic. It took real investigation, checking every other station, ruling out every other explanation to prove it wasn't. That's not a comforting detail. It's a reminder that the difference between a false alarm and the real thing can, for a short window, look identical on paper, and that the people watching this mountain are working quietly to make sure that window closes as fast as humanly possible. Whether it always will is the one question no monitoring network, however advanced, can fully answer in advance.